Hello everyone, good afternoon. I am Yifan from Tsinghua University. Today I will introduce our paper, TGW, Operating an Efficient and Resilient Cloud Gateway at Scale. This is a deployed system paper, and the authors are from Tsinghua University, Renmin University of China, and Tencent. TGW's full name is Tencent Gateway. It's the bridgehead of the Tencent Cloud. TGW is between the internet and the Tencent Cloud data center, carrying all the network traffic between clients and our cloud servers. In addition to the north-south traffic between the internet and cloud servers, TGW also carries a huge amount of east-west traffic of our company services and the internet traffic. As one of the largest cloud providers in China, Tencent Cloud service numbers and gateway traffic have grown at a very fast rate per year. So TGW has also evolved rapidly, both in architecture and scale. Around 2016, we built the current version of TGW based on the DPDK technology. Then we scaled the deployment of our system to our 30 regions and thousands of machines per region. We also tuned and optimized TGW's performance, enhanced its readiness, making it an efficient and resilient cloud gateway, even at a very, very large scale. Actually, we have considered and tested many alternatives, but each of them have some shortcomings and prevent us from deploying them at scale. The first one is the fixed function hardware switches that are used in the traditional gateway. They are cheap but very inflexible. They are not suitable for the changeable cloud services which need private protocol support. Okay, the second one is the XDP. Its advantage is that it runs in the kernel and is simple for our to develop and operate. However, compared to DPDK, it cannot provide enough performance when the traffic volume is huge. So we do not use it for the gateway functions. Instead, we deploy it at the edge host of our cloud CDN. Then there is the VPP. VPP provides rich network functions and good performance. It also uses the DPDK as a forwarding engine, and build an overlay on it. So we do not use it because the gateway functions are logically simple. We don't need another overlay to increase our head. The next solution is the hardware DPUs, FPGAs, and SmartNICs. They offer flexible programmability and can offload the network functions. However, we think they have no cost performance because they have very high power consumption. The last one is the program switches. They can provide very good programmabilities and very good forwarding performance. We have deployed them in our test bed and get very good results. However, they are still highly resource constrained. We can only store a very small part of the rules on it. And second, their outlook is still unclear. There are no clear standards for program chips, and choosing one type will lead us to vendor dependency and even supply chain breakdown like the Tofino chips. Before introduce our design, we need to emphasize our key design principle for TGW. TGW is built for the Tencent Cloud services, so the Tencent Cloud's killer services are online gaming and live stream. So we need to meet the requirements of these users. We need to focus on the latency, jitter, and packet loss between the game players and the servers instead of the throughput. Based on these requirements, we summarize 3 motivations for building TGW. First, we need to get enough performance, especially the latency. Second, we need to dynamically manage our states to deal with bursts and machine crash. The third one is the most important. We need to keep a high resilience to ensure availability. Next is our architecture. The data plane is composed of multiple load distributors we call LDs, and the LD can perform network functions using the forward engine in it and advertise and monitor connection information through the routing module and the healthy module. The statistics agent will connect the logs and report to the management plane. The orchestrator, the operator, and the admin on the LD are top-down management components from the global class local to LD local. The TGW probers and the TGW brains are our failure detection tools, responsible for failure detection and localization. Our workflow is based on the gateway's main function, elastic IP access, we call EIP, and cloud scale load balancing, CLB. For the EIP, we will expose a public IP address called VIP for some similar services and distinguish them by different ports, we call vPort. The TGW EIP's function is to parse the client's packets and distribute them to different services. The other function is CLB. It is located behind the EIP and is responsible for balancing the traffic destined for the same service. Our design divided into 4 parts: packet forwarding, state migration, failure resilience, and failure detection and localization. We arrange different forwarding models for the different network functions. For the TGW EIP, it's a stateless and simple function. So we employ an ATC model for the EIP. Each flow is processed by a single CPU core. This model can minimize the latency and is very easy to scale. For the CLB, we use a pipeline model because this is a stateful function and we need to enable service-specific identifier dispatching. For example, in the game services, we need to keep the TCP and UDP packets from the same clients processed by the same core to prevent the latency jitter. This means that we need to dispatch the packet based on the IP pair instead of the 5 tuples. So we need an extra CPU core to be the dispatcher before we process the packet. The next is our state migration mechanism. We designed it to handle the tricky 80-20 rule. Based on it, we can dynamically migrate the traffic from our loaded clusters to more capable clusters. At the beginning of the migration, we will directly migrate the major connection states from the old cluster to the new one. And then the LDs in the new cluster start to send BGP advertisements, redirecting the traffic. At this time, there will be some not migrated or new connections at the old cluster, but subsequent packets will be forwarded to the new cluster. We use the LD proxy to solve this. If the LD in the new cluster receives an unknown package, it will forward the packet to the old cluster. Since the old cluster has the corresponding states, it will forward the packet to the correct backend server. Note that the old LD will not change the source IP address when forwarding. Thus, the virtual switch in the backend server will learn this IP and send the response packet to the new LD. The new LD will then establish the connection and correctly forward the subsequent packets of this flow. In this way, no packets will be dropped and only a very small number of packets are proxied. For the failure resilience model, we employ different models at different levels. Intra-AZ, we employ an active model between LDs. Each LDs in an AZ cluster will centralize states to keep equivalence, and the live LDs continue to send BGP advertisements to upstream routers, and the routers will distribute the traffic to a live LDs via ECMP protocol. This model can be employed in an AZ cluster because LDs in the same cluster are close in network topology, and centralizing them has lower cost. Inter-AZ, we employ an active standby model. We do not centralize all AZ cluster states because it's expensive, so we need to keep every 2 AZs as a redundant pile. AZs in a pile will back up each other through state centralization, and we carefully configure the rules in the regional routers to redirect the traffic. Each AZ is configured with an active segment and a standby segment. Its active segment has the same address as another AZ standby segment, but has a longer prefix. When 2 AZs are both alive, they will only receive different traffic that belongs to their active segments. But when one of the AZs fails, its traffic will be redirected to another AZ according to the standby segment. The backup-based model can help us recover from many types of failures, but there are still failures that cannot be resolved by it. For example, when an abnormal or malicious flow arrives at one LD, some flags in the packet header will trigger some bugs, some software bugs, and cause our LD to crash. The routers find the LD crashed and redirect the flow to another LD. However, the root of the failure is located in the flow instead of in the LD. The second LD will also be crashed. Then all LDs in a fault domain will be crashed by this flow. Fortunately, we find that this type of failure is usually caused by the traffic destined for a single VIP, so we designed the decentralized migration to partition the traffic and minimize the impact. First, when the failure happens, we will divide these affected VIPs into K parts and migrate them into independent K standby buffer LD sets. Since only one VIP is the root of the failure, one buffer set will be affected and other VIPs will be recovered. If the impact is still large and we can have do one more time decentralized migration, this method can help us to minimize the failure impact and reduce the impact to 1K squared. The last design is about the failure detection and localization. Our solution is to design a tent-based telemetry system. We actively send the probing packets to locate the failure. We deploy many TGW probers on the internet, and they will continue to send probing packets to our backend servers. We set some trace points, the blue one in the figure, at the RX and TX ports along the path of the probing packets and the response packets. When the probing or response package arrive at the trace point, they will be tented by rulers. After receiving the response package, the TGW prober will record the trace point. We also set some drop points, the red one, at the process stages of the LD. When the LD drops a package, the drop point will be triggered and recorded. At runtime, the recorded trace point and the drop point logs will be transferred by the proxy servers. The proxy servers will distribute the logs to the TGW branch by the for tuple. The TGW branch will then analyze the logs and localize the failure in parallel. The results and warnings will then be sent to the orchestrator. We also keep our history logs in our DDBS for future reference. Okay, next is our evaluation. We test TGW in both the testbed and real-world environments. We test our single LD node performance in our testbed and compare TGW's throughput to provoke tripled. We find that TGLab single node has a maximal 40 megapps throughput, which is nearly 2 times that of tripled on the different package sizes and the CPU loads. TGW single node also has microsecond level latency, and the latency does not vary significantly on the most package size and CPU loads. Next, we show our real-world data. The left is the throughput and packet loss rate in a TGW region during a 1-week shopping festival. Our peak throughput can reach tens of TPBs, and our packet loss only happens when the traffic volume is huge and the rate is from 10 to the power of -7 to 10 to the power of -4. The right is the traffic rate between clusters. Different clusters have different capabilities, and you can see that the traffic is well balanced across the clusters over the time. At last, we want to share some experience and lessons during our long-term operation. The first is to isolate the blast radius. We restrict the fault domain by designing a loosely coupled architecture. One component's failure will not affect another component's. We also have some ad hoc failure reaction plans, such as decentralized migration to reduce the impact range of failure. Then we also keep regional independence. Each region has its own states and is managed independently. The second one is redundancy. Redundancy is almost always the best practice to ensure availability. We set 50% of redundancy at each level. At the AZ level, two AZs are a redundant pair and back up each other. At the rack level, we keep machines in an AZ cluster that are distributed across more than 2 racks. At the machine level, we make sure that at least half of the machines can carry all the traffic. At the NIC level, we deploy redundant NICs and fibers, making sure that a machine can tolerate half of the NICs or fibers failure. The third one is the discussion of scalability and portability. We think that TGW scalability and portability have been proved by practice. For scalability, TGW is now scaled to more than 30 regions and thousands of machines per region. For the portability, TGW is not only deployed in Tencent, but we have also deployed it for dozens of customer companies, like including famous banks, TV stations, and car groups. The last lesson is very important and is a key design principle for TGW. The service type determines the properties of the infrastructure. We designed TGW for the requirements of our killer service, online gaming, so we are more concerned about the latency, the jitter, and the packet loss instead of the throughput. We also have some interesting experience and lessons. Please see our paper for details. To conclude that TGW is a mature cloud gateway system for Tencent Cloud. It has been operated for more than 8 years and have scaled to more than 30 regions and thousands of machines per region. It's composed of a DPTK-based forwarding plan, a migration mechanism, a value resilience model, and a telemetry-based value detection and localization systems. Our test-bed experiments and real-world data prove that TGW is an efficient, scalable, and highly resilient cloud gateway. And thank you for listening. This presentation is supported by the Dengfeng Fund of Tsinghua University. Thank you.